I should thank both centers, ICTP and CIMPA, for giving me such an opportunity to be here and give this series of lectures. Especially, I would like to thank people in the math section of ICTP for their kind hospitality, and also my sincerely thank to Professor Arezzo, the head of the department. Okay, let's start. My first lecture is about the algebra. But before starting, I should mention that whenever I say F, F for me is always an algebraically closed field of characteristic 0. And whenever I say I have a vector space without mentioning the field, I mean that I have a vector space and this field F. And for the convenience of audiences, I try to start with very elementary and basic facts, and then step by step I go to the main body of the lecture. So hopefully for people who are familiar with linear algebra and tensor products, hopefully they can easily follow the lectures. Okay, let's start with an easy example. Suppose that V is the vector space m times n over R, and n is a positive integer. V is the vector space of all matrices which are n times n, and entries are from R. We know that it is a vector space, so we have a summation and we have a scalar product, and these two guys are compatible. Compatible in the sense that R A plus B is RA plus RB, RSA is R SA, and so on. But we have a usual product of matrices. I use this usual product just by juxtaposition. For me, AB is just the product, the usual product of two matrices. And this usual product satisfying associativity. It means that ABC equals ABC. And this usual product completely compatible with this summation and this scalar product in the usual sense. So we have a vector space, we have an extra product, and this extra product satisfying this condition, which is associativity. We simply say that we have an algebra which is associative. Algebra means that a vector space with an extra product, and these products are compatible, and associativity means this condition. Now let's look at another example. An easy example. Suppose that V is R3. Again, R3 is a vector space. We have a summation, we have a scalar product, and we have an extra product here, which is cross product. We know what is the cross product of two vectors in R3. In fact, if we make a fist using your right hand, and then make a fist from the direction from A to B, your thumb has a direction. This direction is the direction of A times B. A, B are two elements of R3, and AB I told you what is the direction, and it has a specific length, and then we know what is A cross B. We know that A cross B is not associative, but instead it satisfies this property. A cross B cross C equals A cross B cross C minus B cross A cross C. A cross B cross C minus B cross A cross C equals AB cross C. We refer to this property Jacobi identity. It is one of the properties that this cross product has. Another property, if you make A cross B and then B cross A, these two guys are completely opposite of each other. We refer to this condition anti-commutativity. So we have a vector space, we have an extra product, and this extra product satisfies anti-commutativity as well as Jacobi identity. So we have a vector space, we have an extra product, so we have an algebra. And this algebra satisfies anti-commutativity and Jacobi identity. We say that we have a Lie algebra. Okay? Let's look at another example. Again, suppose that V is the vector space of n times n matrices over R. We have the usual product of two elements, AB over B, but I want to introduce a new product. We have AB, then we also have BA. I make the subtraction and call it A star B. So I have a vector space, I have an extra product that I make it in this way. I have AB, I have BA, and then put minus between these two and call it A star B. And again, it is obvious, if you change the order of AB, you get the opposite. So again, we have A times B equals minus B times A. And as an easy exercise, you can show that A star B, A star C equals A, B, C minus B, A. Again, anti-commutativity and Jacobi identity. It means that we have, again, a Lie algebra. Okay? So we have a vector space, we have an extra product. If this extra product satisfies associativity, we say we have an associative algebra. And if this extra product satisfies anti-commutativity and Jacobi identity, we say we have a Lie algebra. Okay, let me write down the exact definition. Suppose that E is a vector space and star from V times V to V is a bilinear map. Bilinear means that it is linear in each component. In this case, we say we have an algebra. The algebra V star is called unital if there is an element, I call it 1, belonging to V, such that A star 1 equals 1 star A equals A for all A belonging to V. We say that V star is commutative if for all A and B belong to V, A star B equals B star A. We say that it is associative if A star B star C equals A star B star C, and we call it Lie algebra if A star B equals minus B star A and A star B star C equals A star B star C minus B star A star C for all A, B, C belongs to V. And I told you some examples of Lie algebras and associative algebras. I should mention one point. Traditionally, when we have a Lie algebra, the product, we refer to this map, the product. The product is denoted by brackets. Instead of a star, we write AB. AB, it is just traditionally used. That's the product on the algebra is just denoted by brackets. Okay. After this definition, let's look at another definition and then some examples. Suppose that A and a star is the product on A, is an algebra. And I should mention that sometimes I omit a star and instead of A star B, I just write AB, just for simplicity. Suppose A star is an algebra, a subspace B of A is called a subalgebra if for each two elements A, B belong to B, AB is an element of B. A space I of A is called an ideal of A if AB belongs to I and BA belongs to I for all elements A of A and B of I. We call it I. And when we say that our algebra is simple, it means that the only ideals are the trivial ideals. In fact, if AA is not 0 and 0 and A are the only ideals of when we have a subalgebra, we denote it with this notation. And when we have an ideal, we denote it with this notation. Okay, let's look at some example. It's better to write it as an exercise that you can do it by yourself. Suppose that A together with the product S star is an associative algebra. Show that A together with the following product A times A to A that maps AB to A star B minus B star A is a Lie algebra. In fact, you should check anti-commutativity and Jacobi identity. Anti-commutativity is trivial because you just change the order of A and B, and when you change the order of A and B, you get the opposite one. So it is clear that anti-commutativity is satisfied, but you should write something to show that the Jacobi identity is also satisfied. Okay, this Lie algebra that comes from an associative algebra is denoted by a bar. Okay. For example, suppose that A is the set of all n times n matrices over F. A together with the usual product of matrices is an associative algebra. So, according to this exercise, A bar is a Lie algebra. So, A bar is a Lie algebra. In fact, A bar is n times nf, but the bracket is AB minus BA. This Lie algebra is denoted by GLNF. Another example, suppose that we is a vector space and sets A to be all endomorphism of B. Again, endomorphism of B together with the function composition is an associative algebra. A together with this circle that I mean composition is an associative algebra. So A bar is a Lie algebra. This Lie algebra is denoted by GRFB. Please don't hesitate to ask me if you have any questions. Okay, let's look at another example. Set SL and F and is an integer number that it is greater than 1. SL and F, we say it is the set of all elements of GL and F such that the trace of X is 0. By trace of a matrix, we mean the summation of all the diagonal elements. Okay. And if we look at this, let's say something. If X and Y are two elements of GL and F, then trace of X, Y. I remind you, the brackets in GLN is just commutator, xy minus yx. So it is trace xy minus yx. And we know trace of xy equals trace of yx. And trace is linear, so it is 0. It follows that SL and F is an ideal of GLN. Okay? And as an exercise, please show that SL and F is a simple algebra. It means that SL and F doesn't have any non-trivial ideal. The only ideal is just SL and F and 0. Okay. In general, finite dimensional simple algebras are classified and now as types AN, BN, CN, EN, E6, E7, E8, F4, and G2. And SL and F is a simple algebra of type AN-1. I told you that here n is greater than 1, so n-1 is meaningful, and SL and F is simply algebra of type AN-1. Okay, any question? No? Good. Let's look at another example. Suppose that G is a Lie algebra. Set G tilde to be G tensor product of Laurent polynomials over F. I claim that this G tilde is also a Lie algebra. For this, I need to have a Lie bracket. I will define the Lie bracket and this G tilde. To emphasize that this Lie bracket is related to this G tilde, I denote it by bracket tilde. Define this tilde from G tilde times G tilde to G tilde in this way. The bracket of X tensor Tn, Y tensor Tn is defined to be the bracket of xy is in the bracket over G tensor Cn plus n. Okay? Very natural. The bracket of x tensor Tn, y tensor Tn is just bracket of x, y tensor Tn plus n. And as an exercise, please show that it is a Lie algebra. Anti-commutativity is trivial because the bracket on G is anti-commutative, and for the Jacobi identity, you need to write some lines, and then you can get that this is a Lie algebra. G tilde together with this Lie bracket is a Lie algebra. I think I shouldn't use the red color because maybe people cannot. Oh, yes. Okay. I think it's not visible for people online. Let's look at another example, and we try to check it together. It is another example of Lie algebras. Suppose that G is a Lie algebra. I denote the bracket also. It's a Lie algebra. And we have a bilinear form from G times G to F. Is a bilinear form, and this bilinear form is symmetric and satisfying this property. The bracket of x, y, z, F1 is y, z for all x, y, z belong to G. This property is called invariant. We say that the form is invariant if this condition is satisfied. And I assume that I have a Lie algebra and the bilinear form. This bilinear form is symmetric and invariant. Then assume C, my field is F, FC direct sum FD is a two-dimensional vector space. Since G hat to be G tensor product F C plus minus 1 F Laurent polynomials over F direct sum C. Oh, I again wrote C. FC direct sum FD. I claim that this G tilde is also a Lie algebra. What is the bracket? Define. I denote the bracket by bracket hat to emphasize that this bracket is for this G hat. From G hat times G hat to G hat. Okay, I define E to be 0, and everything is 0. D and its tensor Tn is its tensor Tn with coefficient n, and the only thing that remains is the bracket of the elements of this part. I define X tensor Cn, Y tensor Tn. Please be careful about the thing that I want to write. It is defined to be bracket of xy tensor Cn plus n. Till now, I haven't used the bilinear form. And now the bilinear form appears plus n delta n plus n0. It is Kronecker delta, the form of xy, and then c. Okay? I claim that G hat together with this bracket is a Lie algebra. Is it something that you want to write?
Yeah. What is the summation?
Plus n.
Okay.
Yeah. Delta. It is the power of this n delta n plus n0, the bilinear form of x, y, and then c. Okay, and I claim that this G hat is a Lie algebra as well. It is a bilinear map, so the only thing that I want to see together is the Jacobi identity. You can see the anti-commutativity by yourself. Define this. We claim that G hat is a Lie algebra. Okay. We need to look at X tensor Tn, Y tensor Tm, and Z tensor Tk. Let's look at this. It equals, here we should write from this, it is xy tensor Cn plus m, and there is some part about c, but the bracket of c with everything is 0, so I can omit this and write this. I have another bracket here, so I can omit c from this one. And then look at this. What is this? It is xy z tensor Cn plus m plus k, and then plus n plus m delta n plus m plus k 0, and then x, y, z, c. Okay? Let's end it. It's equals, okay. Here we have this, and we can use the Jacobi identity for this. So I write it in this way. X, y, z minus y, x, z tensor C and M K And here I have n plus m. I write it in this way, n delta n plus m plus k 0 x y z c plus m delta n plus m plus k 0 x y z c. Okay, but let's look at this. Our bilinear form has a property. I told you it is invariant. So the bracket of x, y, z, because it is invariant, it is x, y, z. And moreover, the bracket of x, y, z, as the bracket is anti-commutative, we can write it as minus yxz, and then as it is invariant, it is yxz. So this part and this part can be written here. I can write it x, y, z, and here I can write it as minus yx. Okay? So I use the first part and then this part together, and then use this part and this part together. What I will have is this. X, y, z, so Cn plus m plus k plus m delta n plus m plus k 0 x, y, z, c minus y, x, z, so Cn plus m plus k minus m delta n plus m plus k y x z c. But the first one is nothing but x tensor Cn, yz tensor Cm plus k Cm z tensor Ck, and the second one is nothing but y tensor Cm x tensor Cn z tensor Ck. And it is something that we need for proving the Jacobi identity, right? It is a very easy example, but it is one of the most important Lie algebra. If G, we start with a G, and if G is simple and finite dimensional, and over the complex numbers, this G hat is called an affine Lie algebra. In affine Lie algebras form a very important class of Lie algebras. Okay, and you saw that the construction is not so difficult.
So G hat, the general element of G hat can be expressed by, let's say, x tensor Tn plus linear combination of C and D, right?
No, the typical element is in this form. G hat is G tensor if X is an element of G hat, X is upon Xi tensor Ci plus RC
Then,
there is a summation here.
yes. Okay. Then, in order to prove the Jacobi identity for this element of G hat,
Yes.
the starting point, if you remove the linear combination C and D. Of course, C can be removed because C hat is everything 0, but D is not 0.
Yeah, I define the bracket just for this element, and this element, generating set of this element. And then you can linearly extend it. Okay? And as the bracket is bilinear, when you want to verify the Jacobi identity, it's just enough to check it for the elements of each part. I mean, just because it's a vector space. Okay? And the bracket is bilinear. If you have something like this, summation, or I'm talking in general, something like this, Sj, Bj, it is summation Ri, Sj, Ai, Bj. Okay? Because it is bilinear. And when you want to check the Jacobi identity, it is enough to check it just for these elements. And then, because it is linear and in fact bilinear, it is true for all elements. Okay?
At least we need to start with like x tensor Tn plus D.
Sorry?
So
Let's check it together. Let me one element that we check it together.
X tensor Tn plus D.
Something like this.
And I think everything. Yeah,
Okay. And then say something, let me write it in this way. You mean something like this, yeah?
Yes.
Okay. What is this? It is X tensor Tn because it is bilinear, so I can write it in this way. Plus dA and B.
Yes.
Okay, and then X tensor Tn A, and then dA. I show you the.
So the first part is okay.
Okay.
Yeah.
And you,
yeah.
you should check it by yourself. I told you, I just tell you about one of the parts, and the other parts you should check it by yourself for B and C. And you're right, C is trivial because it vanishes everything. Yeah, and it kills everything. I show you the most difficult part. Okay.
Thank you.
Okay. 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 Let's look at another definition. Suppose that A and B are two algebras. A linear map phi from A to B is an algebra homomorphism if phi AB equals phi A, phi B for all AB belongs to A. And just be careful that the product on the left-hand side is the product on A, and the product on right-hand side is the product on B. Okay? And okay, and when we have the definition of homomorphism, we can define monomorphism, epimorphism, automorphism, and endomorphism in the usual sense. When we say we have a monomorphism, it means that we have an homomorphism which is injective. If we say we have an epimorphism, it is a homomorphism which is surjective, and so on. Let me give you another exercise. Please show that if G, it is a very nice exercise. Suppose that G is a finite dimensional Lie algebra a three-dimensional algebra such that G equals bracket of G. I mean that a span of F for all two elements. If the algebra satisfying this condition, we say that G is perfect. And I assume that G is a three-dimensional Lie algebra, which is perfect. And the point is that using this, show that there exists x, y belongs to G such that x, y is not zero. Okay? If G is a three-dimensional Lie algebra, which is perfect, then you can find two elements x, y, such that this bracket is not zero. As an exercise, try to find these two elements. Suppose that G is a Lie algebra. And B is a vector space. We have a Lie algebra and we have a vector space. When we have a vector space, we can talk about here. Just, I should mention that we have a Lie algebra in general. I don't know what is the Lie bracket on G because it is a general Lie algebra. But here we have GLFD, and we know what is the bracket on GLFD. Okay? A homomorphism phi from G to GLFD is called a representation of G in V. Okay? We have a general Lie algebra G, and we have a GLFD here, and a homomorphism from G to GLFD is called a representation of G in V. And if this V is finite dimensional, we say that our representation is finite dimensional. Okay, let's look at an example. Assume G is a Lie algebra. G is a Lie algebra, but G at first is a vector space. So I can form GLFG. Add from G to GL, which maps X to add of X, where add of X is a map from G to G, mapping Y to XY, is a representation of G in itself. Okay, and let's check it together. I told you, when we say we have a representation, it means that we have an algebra homomorphism. So it must be a linear homomorphism, and it should be an algebra homomorphism, okay? And you can do it by yourself, that this F is linear, okay? It is a linear homomorphism, and I just show you that it is an algebra homomorphism. It means that it preserves the brackets. We should think that add of xy equals add of x, add of y. Again, I mentioned that we don't know about the bracket on G, but we know the bracket on GLF. The bracket in GLF is just the commutator. So the right-hand side, it is just add of x, add of y, minus add of y, add of x. And we should prove this. And these are maps from G to G. And if we want to prove that this map equals this map, it is enough to apply it on one element, one typical element, okay? For each Z, belongs to G. The left-hand side is add of xy over z. It is, according to the definition, add of x maps y to bracket of x and y. So add of xy over z is the bracket of xy and z. And now we can use the Jacobi identity. What is this? It is x, y, z minus y, x, z. Okay? But what is it? It is add of x, and what is it? It is add of y. Then minus add of y, add of x, z. And it is something that we need. I prove that add of xy equals add of x add of y minus add of y add of x on a typical element. So we have this one. This representation is called adjoint representation. I gave you an exercise. Let me recall it one more time. The exercise was this. If G is a Z algebra, dimension of G is 3, and G is perfect, then there exists x, y belong to G, such that add of x3, which is x, y, that's it. Okay, it is the exercise I told you. And now I want to prove some level. If G is a three-dimensional algebra, which is perfect, then G is isomorphic to SL2F. Okay? In fact, up to isomorphism, we just have one three-dimensional Lie algebra, which is perfect. And just mention that suppose that G is a simple Lie algebra. If G is a simple Lie algebra, it is perfect because the right-hand side is an ideal. And when we say that G is simple, the only ideal is 0 and G. And as we know that simple Lie algebra, for a simple Lie algebra, the bracket of G with itself is not 0. So if we have a simple Lie algebra, G must be equal to bracket of GG. And so this lemma says that the only simple Lie algebra of dimension 3 is SL2 up to isomorphism. Okay? Let's look at the proof. let's first look at SL2F. What was SL2F? SL2F is O 2 times 2 matrices with trace X is 0. So, I think you believe that dimension of this space is just 3, because we have 4 elements and we have a relation. So the dimension is 3. And let me tell you a basis. Put E to be 0, 1, 0, 0, F to be 0, 0, 1, 0, and H to be 1, 0, 0, minus 1. These 3 elements are elements of trace 0 and are linearly independent. So these 3 elements form a basis for SL2F. Okay? And we can see that it is very easy to see that the value of each element with itself is 0, and EF is H, HE is 2E, and HF is minus 2F. And the bracket of each element with itself is 0, because you know the bracket is anti-commutative, and so XX, it was minus XX for each element, and as the characteristic of the field is 0, and we have here 2XX is 0, so the bracket of each element with itself is 0. So we know the Lie bracket just with these relations. Okay, now suppose look at our G. Okay, here we told that we want to use this exercise to prove this lemma. At first, X a non-zero element of G, and then extend X to a basis of G. For example, X, Y, Z. Now look at adult X. Adult X is a map from G to G. And we have an ordered basis here. So we can write the matrix of adult X with respect to this basis. And what is this? Let me call it V. The matrix of adult X with respect to V is of the form as adult X over X is the bracket of X, it's 0. So the matrix of adult X with respect to V is of the form this. Something like this. That's okay? If you you have any question, please ask. We have, in fact, add of x over x is the bracket of x, which is 0. So the first column is 0, and the other columns, I don't know what is it. It is, for example, ax plus by plus cz, and add of xz is a prime x, b prime y, c prime z. So the form is of this form. And so the characteristic polynomial so there is a scalar a characteristic polynomial of add of x is lambda 2 minus 6. But there is at least one edge belongs to G such that C edge is not 0. Why? If for all edge C edge is 0, we always have lambda 3 equals 0. Lambda 3 is the characteristic polynomial of add of x. And so if the characteristic polynomial of all add of x is lambda 3, it means that add of x3y is 0 for all elements xy. I'm using Cayley-Hamilton theorem, okay? And in the previous exercise, I showed that such a thing does not happen, okay? So we have at least one edge such that C edge is not 0. So for this edge, the characteristic polynomial is lambda 2 minus C edge. Characteristic polynomial has 3 different roots, and so it is diagonalizable. So there exists E and F such that E and F of G and R and S belong to F minus 0 such that add of H over H, we know it is 0, add of H on E is RE, and add of H on F is SF. Okay. And now, let's look at the bracket of EF. Suppose that EF is an element of G, and G is spanned by HEF. So there exists M and P belong to F, such that the bracket of EF is ME plus NF plus PH. And then bracket of HEF, instead of EF, we can put this, and bracket of H is this. The bracket is linear. It is MHE plus NHF plus PHH. It is 0. HF is SF and HE is RE. So we have MRE plus NSF. Okay. And what we have now, it is we have this one, and also we can use the Jacobi identity. And the other hand, HEF equals HDF plus EHF, which is just the Jacobi identity. HE is RE, so we have RHF. HF is SF, so we have SEF. And so we have R plus EF, and EF is just ME plus NF plus PH, so it is R plus S, ME plus NF plus PH, and these two guys must be equal, this one and this one. And you remember that EFH form a linearly independent subset. So we get that P is 0. And then we have, okay, yes, we have P equals 0. We have MRE here, and we have MRE here. Yes, R plus SM equals RM, and R plus SN equals NS. I think, yeah, I think this one here as well. RSP is 0, and this implies that R equals minus S, and RM and S is 0, M equals N equals 0. Okay, so what we get, it implies that bracket of EF is just M is 0, N is 0, and we have just PH. Okay, and we also have that R equals minus S. So what we have, we have EF equals PH, we have HE equals RE, and we have HF equals minus RF. And now, and we know that P is not 0, and then set H prime to be 2R PH, E prime to be two over R E with some coefficient here, and F prime. Let's check it. We have E prime F prime equals 2 over R EF, and the bracket of EF is P H. So we have 2R PH, and it is just H prime. Okay. And we have H prime E prime. It is 2 over R P H. What is E prime? E prime is a square 2 over R E. And what is this? It is 2 over R, 2 over R P. And what is the bracket of HE? It is RE. We have this one and this one. Maybe we need, okay, I need something. Let me P, if we put P here, we have P here. And instead of this R, I should put, I think, RP here. Let's check it for this. Yes, I think we should do this, and then for this new E prime F prime, it is 2 over R. We have EF. Yes, exactly. What we have here, we have E prime is this, and we have 2 over RP, bracket of EF is PH. So we have here 2 over RH, which is H prime, and the bracket of H prime. E prime is H prime is 2 over R H what is R E prime? R E prime is radical to RPE, and it is 2 over R, 2 over RP G, and it is RE, and it is 2 over RPE, and it is 2E prime. And similarly, you can see that the bracket of H prime, F prime, plus minus 2F prime. So we have 3 elements, H prime, E prime, F prime. E prime, F prime is H prime. H prime, E prime is 2E prime. H prime, F prime is minus 2F prime. So you can define now phi from SL to F. So this G map. You remember I wrote 3 elements, H, E, F. H maps to this H prime, E maps to this E prime, and F maps to this F prime. And then this phi is exactly an isomorphism. So we show that the only simple algebra of dimension 3 is SL2, and more general, the only 3-dimensional algebra which is perfect is SL2. Okay, let's stop this lecture now and then continue at 12, I think. Yeah.